So let's start this course by a very general introduction. So why is it interesting at all? Why should it be interesting at all for a life scientist, a computational biologist, or a biotechnologist to know quantum mechanics? So quantum mechanics is the fundamental theory of nature at the most microscopic level we've been able to access, experiment to this point in our evolution. So in other words, whenever, over the course of the last 4 centuries, humanity has developed techniques to investigate methods, matter, the behavior of matter through the scientific approach. And in doing that has developed technologies to look at nature and the surrounding at smaller and smaller and smaller scales. Galileo was using meters to measure falling objects from Pisa Tower. And today we use accelerators as large as the Garda Lake nearby here to investigate the behavior of matter at scales that are thousands of times smaller than the size of a nucleus, and something like 10 to the minus maybe 18, 17 meters, at least. So you see, over the course of history, mankind has tried to look at the behavior of matter at smaller and smaller time scales in times and space, going down, 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 down. And at some point, discovering that something we are familiar with, the way we look at the world, what we see in the world, changes completely when we pass some kind of a soft wall, which goes from what we call today the classical realm to the quantum realm. And if you watched the movie on Ant-Man, you heard the word quantum realm, although the movie is scientifically completely incorrect. That's fine. So what am I saying? To be more specific, let me draw a diagram here. And on the x-axis, I will put time. And on the left axis, I will put length. So what I will draw, both of these axes are supposed to be in logarithmic scales, meaning that I'm looking at decades here. So for seconds, and this is maybe 10 to the minus, I don't know. What's the femtosecond? That means milli, micro, nano, pico, femto, times 3, 10 to the minus 15. Say here we're like 10 to the 1 second. And of course, there are many techniques in here. And so let's talk about length. We will put some very, 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 very microscopic scale down here, 10 to the minus 15 meters. So now I'm shifting this a little bit above. We talk about 10 to the minus 15 meters. And let's say we go as far as 10 to the 0. That means 1 meter over here. And here there are many things as well. So in this diagram, we compare scales, time scales versus length scales. So different objects in the universe live on different places in this map, right? For instance, us. We are more or less on the meter scale. Our everyday experience ranges from centimeters to perhaps meters, a guitar, a bed. course, we can think about hundreds of meters, but our biology, our interactions are most likely on our scale. That's where we function best. And so I draw a human here. And since I'm a childish guy, I will draw a human like a child because I cannot draw any better than this. So that's us. Now, when you start looking at nature, and in particular, I will focus on matter in the universe that is relevant for life, because this is, of course, for computational biologists, after all, life scientists. You know, you can go and look at things that happens on a smaller scale. At some point, now I'm not going to draw exactly where, don't take this too quantitatively, but there are going to be, I don't know, bacteria. These are the flagella. Then there are going to be other kind of cells. And then as you move towards smaller time scales, at some point you hit the atom scales at 10 to the minus 10 meters. That's somewhere here. And that's a little bit larger than 10 to the minus 50. And then if you go even smaller, then you get the nucleus here. I'm drawing the nucleus like many people do with the, you know, red and blue balls denoting nuclear protons and neutrons. Now, somewhere in the middle here, there are biomolecules. Let me draw something like, I don't know. What I'm going to draw now is supposed to be a cartoon for a protein. This is some kind of a native state of a protein. Don't ask me to be more precise than that. So here is biomolecules. Here is like cells. Here are organisms, and here are like animals. Now, I think we all have seen enough sci-fi movies to know that somewhere around here, in the very lower left bottom of this diagram, things don't quite work the way we are used to in the upper right. That's what we see every day. Somewhere here is the behavioral matter changes completely. And this is the quantum realm. So I'm going to draw this. There's going to be a fuzzy. Are you going to use a different color? I don't understand why gray keep on popping up. There's going to be kind of a fuzzy interface, because things don't just change all and nothing. It's not like we ice water transition. You go, you know, it's quite sharp. The transition of how nature behaves is soft. It's more of a crossover. You'll begin seeing that, you know, things start to change a little bit, but not too much. And then all of a sudden they have changed completely, but very, very gradually on the scale. And this is the quantum realm. And this is the classical realm. So anywhere on this side of the world is completely well described by Newtonian mechanics, which is what you have most likely been exposed to in high school and in your education, along with, say, Maxwell's law for electromagnetism and Newton's law for gravitation. So basically, once you know a little bit of electromagnetism, a little bit of gravitation, Newton's law, you're in principle equipped to understand the world around us. With the sort of non-trivial leap of, you know, thermodynamics, which is basically mechanics of many, many, many particles. But that has been understood in the framework of classical mechanics. So you can rederive thermodynamics from classical mechanics using statistical concepts, as we shall see in this master course. So everything that happens here on the upper right side of the platform here is well understood in terms of mechanics and electromagnetism. And none of what happens beyond the wall, the yellow wall, can be understood simply relying on those concepts. Now, I want to emphasize where the wall is. The wall, the boundary of the boundary of the classical realm and the quantum realm is exactly where the nanomachines of life are located. You know, protein or a nucleic acid is characterized by typically a size of the order of, since once it is compact, say a few nanometers. So we're talking about one step up in order of magnitude from the atomic scale. That's where the quantum behavior is clearly there, because atoms, as we shall see in this course, cannot be understood in terms of classical mechanics. They wouldn't exist if the world was classical. We're going to prove that. With only classical mechanics, an atom would collapse in the time of it wouldn't be stable. It would collapse and radiate away all of its energy. There would be no matter. So we know that atoms are quantum. And biomolecules sit in this interface. And to be more specific, biomolecules are, of course, chemical compounds. They're made of electrons and nuclei. And we shall see this in the course, but let me just run ahead and anticipate that the dynamics of electrons and the way they form bonds and the way they distribute in a molecule is not to be understood within the context of classical mechanics, cannot be understood in the context of classical mechanics, but can be understood in the context of quantum mechanics. On the other hand, you might think that all of these electrons around in a molecule, all they actually do is to keep atoms together and perhaps generate interactions between atoms, modify the interaction between atoms. Let me give you an example. You have, say, oxygen and hydrogen forming water, and the electrons are shared according to the laws of chemistry, and the net result is that there's an effective force keeping the oxygen and the hydrogens together with a given geometry, which is dictated by quantum mechanics. But everything goes as if the oxygen was not completely neutral, had a little bit of charge, and the hydrogen were not completely neutral, but had a little bit of charge because the sharing of the electron is not completely uniform. So now, if you take away this quantum information, quantum part of the structure, which is entirely quantum due to the electrons that are not classical, you can think that the nuclei are actually subject to some forces that are due to quantum mechanics, and you will discover in this course that the dynamics of this nuclei is to a very large extent classical. So basically, when you have a macromolecules that evolves, it evolves like a classical object, but such that the forces between the particles, the centers of the atoms, are explained only in the context of quantum mechanics. So I would say the dynamics of particles is classical, and the forces are due to quantum mechanics. Now, whatever I just said now is just a piece of information I'm giving to you without asking you to know why. You should not be able to see why it is that. We will be able to see this, why this is that, later on in the course, much later on in the course. At the moment, I'm giving this to you as a fact. Buy that, learn it. Now, I find it fascinating, to a point that drives me crazy sometimes, to think that nature is based on nanomachines, right? I mean, basically, you have a microscopic scale where the chemistry and the elementary processes that are responsible for life, say gene expression, transcription, and all that, are performed. But typically the environment changes on a much longer time scale. It starts to rain, food becomes available, all the macroscopic changes that happens at the scale where the organisms live are many orders of magnitude away. So basically, organisms equip themselves with nanomachines that can perform and operate at the scales where the chemistry takes place. So basically, life has developed in such a way that is based on nanomachines that operate at the last possible classical scale before you enter the quantum realm. I found this amazing. The nanomachines don't operate at this level, and then there's nothing more for biology. Biology, so to say, starts at the beginning of the quantum realm. And the first thing you ever do, probably as a biochemist, is to learn about the peptide bond or something like that. That happens right here. So this discussion says that if you really want to understand biologists, the reductionists approach, meaning starting from the fundamental building blocks and going bottom up in building your understanding to biology, you really have to start from the quantum mechanics to understand the forces between atoms and then move on. As we shall see in this course, the very existence of matter is due to a phenomenon called quantum tunneling, which is often seen in sci-fi movies. It's a particular phenomenon that doesn't happen in classical mechanics, but it does happen in the quantum realm, and is responsible for generating the attractions that is responsible for the chemical bond. So without quantum tunneling, there would be no chemical bond, there would be no molecule, there would be no protein, no nucleic acids, and ultimately there would be no life. So you see, we are facing here rooting biology to the fundamental laws of physics. Now, this might seem an interesting conceptual trip, intellectual pursuit. And of course it is. I find it enormously relevant for scientists to have some knowledge of this, no matter whether later they work on online sequences for that. Protein sequences, or I don't know, they work on the lab. But there's more to it. It is also important if you want to build a reductionist practical approach to investigate biology through physics, or as it sometimes is called, biophysics or biological physics, or whatever you want to call it. And here we open a huge discussion, which I will only scratch, of course. We'll look at the reductionist. Or reductionist biology versus systemic biology. Now, anytime you split the world into big categories, you're bound to oversimplify things, and you are prone to be criticized. And everything that I say, whenever I draw bigger distinctions, is to be taken with a lot of caution. But let me tell you what I mean by this. Biology is the land of complexity. We all know that. What is complexity? Well, if you Wikipedia the complexity, you'll find a number of definitions, and if you look on the web, the word complexity is being used even in science to mean different things. But as a working definition, we might agree or not, but we're going to use here just for sake of argument. We can think about complexity as property of a system which is made by many, many, many pieces, many what will be becoming later degrees of freedom, and many entities, but in such a way that the global properties of the entities, of the system, cannot be understood as just adding up one next to each other the properties of the constituents. Let me give you a counterexample. much of the behavior of an ideal gas in a box can be understood thinking of particles being completely independent to each other. So now if you understand the properties of a single particle and probably understand that there's a statistical behavior in that, then you can reconstruct most of the property of an ideal gas. On the other hand, this is very far from what happens in biology. Living organism is not just the properties of a living organism are very far from the properties of the atoms that compose them. In other words, take a bunch of carbon, oxygen, nitrogen atoms, put them in a box, and they don't make a living organism by themselves. Atoms are not alive objects. Life is an emergent phenomenon which results of the complexity or reflects the complexity of matter when you put all these different type of matter and let them interact among themselves. Now, when I say this, I refer to this specifically because once we face the land of complexity, we are in front of a split intersection, a crossroad. We might turn right or turn left. So at these intersections, the reductionist turn, let's say the left turn, is the following. Okay, we have a complex behavior. The only way to make sense of that is to start splitting down and to find how each scale, once you build from the most microscopic cell, and you see how most microscopic objects get together, and you understand what is the smaller entity they form, say you go from atoms to molecules, and then you understand everything you can about the molecule, and then you make the next step, is how molecules interact together. And then once you have a few molecules interact together, you build another layer. You understand how different groups of molecules interacting together cooperate to form, say, a cell. And then you move forward. This is the reductionist. It's based on the idea that you can grasp some insights by breaking things to the simplest possible level. Physicists love reductionists. I would dare to say that's all we can actually hope to be doing. And since we don't want to be unemployed, we love reductionism. But my colleagues with whom I work, they always tell me, you're completely crazy to hope in reductionism. And they have a big point there. They say, life is so intrinsically complex that you'll always be facing the fact that you're missing variables, you're missing information, you will never have control on the physical system. So even if you were able to control theoretically all these parts will interact, you'll never have the information of what they are, how they're distributed. And there's no way you can reduce a problem as complex as a living organism to a set of elementary components interacting themselves. It's much better to take a top-bottom approach, forget altogether about how the inner structure is, and try to understand some knowledge, to gain some knowledge about how this collective behavior happens. Maybe, let me give you an example. If you want to understand the role of a protein, or understand the pathology, then the reductionist will start from looking for the proteins that are involved in the, say, path signaling associated with that pathology, and then try to model their interaction, and try to reconstruct from microscopic basis the molecular interactions responsible for the, say, signaling pathway. The reductionist approach. The systemic approach will be based on trying to establish correlations between proteins from the top and say, oh, I see that this protein is always activated and expressed in conjunction with the other proteins. And typically this happens in conjunction with that. And then I build networks of interaction trying to, from the top bottom, to understand which proteins are involved in which process, and then later on gain further. I'm oversimplifying things in a horrible way. But the point I want to make is that you can go bottom up and top down. And what is best? Well, there is no best. There's some information you can gain from one part and other information you can gain from the other. And I think the contemporary biologists should be equipped with tools to approach both methods, both schemes. Now, typically, most of computational systemic biology is done via bioinformatic tools. And that's part of your education in this master course. What I would be concerned with is to set the stage of a reductionist approach. And the hope is that with both hands, reductionist and systemic, in the same lab, in the same physical system, you get enough tools to advance the understanding of a specific biological problem. So to be specific with the course that is being given in Trento 2020, there will be a number of courses, and let me draw again the time and length. So my course will be here across the quantum realm. Next year, the course in computer simulations will take over in the classical regime here and learn about doing molecular simulation. And learn a little bit of statistical approaches in mechanics. And then there will be advanced courses for those who really become physics freaks and really want to know more about advanced methods and that allow you to grow a little bit larger in size, for instance, and study larger systems and try to, because the effort, the challenge for the reductionist is to go as far in size as possible, because at some point you run out of computer power because the system becomes so large that it involves so many particles that cannot be fit even in the memory of your computer. So there are methods to try to, coarse-grain the system in wise ways or using very sophisticated algorithms or mathematics to solve these problems. And this is the third year in theoretical methods for soft matter. So you see, we are, in Trento at least, we are unique in the sense that we cover a huge amount of topics, and we basically cover all the reductionist approach within the same master program. And so one can go from understanding atoms down to coarse-grained models for biomolecular membranes or systems. Okay. So this is to put things into a broader context. I'd like to close this lecture, introductory lecture to quantum mechanics, and to emphasize the most difficult challenge that one needs to face in order to implement this program. So this is the program for understanding macromolecules from the fundamental approach and your roots in quantum mechanics, right? That's what we'll be discussing up to now. And once you get out of the realm, then you can use classical mechanics, but you're relying on concepts and some of the tools you have to have in the back of your mind that come from the quantum realm. But what is the big challenges? From the intellectual point of view or from the learner's point of view, which to me are the same concept. But one is hard math. And there's no way to hide it. If you have a reaction like a self-immune reaction anytime you see a mathematical equation, then this can be a big challenge for you because there would be more math than most of the life scientists have been exposed to in their education. And it takes some time to get up with it. So we discussed this already in the introduction to the course. There are good books, there are lectures around. We offer in Trento specific background information, but But there's no really simple way out. Some of this math will have to be mastered by you. But there's a one more point you probably haven't thought about that way, and will be equally challenging for everyone. And it's the fall of intuition. And this is what makes this subject at the same time hard sometimes, but also incredibly exciting on the other. Things don't work as we are used to be seen in our lifetime experience. So whatever intuition we have developed since the age of 2 to interact with the world and make sense of what we see, make sense of the experience, they break down at the microscopic way, at microscopic scale. Just simply doesn't work their way. And so very often we get lost because we keep on thinking classically when we should thinking quantum mechanically. But we're not used to think quantum mechanically. I don't know if you guys are young enough to have had the experience of watching your maybe smaller brother in his 1 to 2 years of age. What kids at that age are busy doing most of the day is this: smashing things together, making noise, rolling things from one end to the other. Maybe they cannot do this because they drop it, but they interact with the world and in a very heavy way sometimes. And why do they do that? Because they are building their intuition, their physical intuition of the world. You build the knowledge that if you smash your head to the hole, to the wall, you're not going to go through the wall. Most likely, you're going to hurt your head. You build the knowledge that you can fall, that you can stand, then you can stretch, that something is either here or here, but it's not here and here. All of this is to be thrown away in the quantum realm. Things are both dead and alive. They are in different positions at the same time. So some of you, you're far too young, but I grew up, I belong to the generation of Back to the Future movies. I was a teenager when they came out. And there's this fantastic scene when they have to cross a bridge and there's no bridge. There's just the hole in between the road because the bridge hasn't been built yet. And they're supposed to go to the other side. And of course, the young guy there is worried to fall into the hole. And the scientist, the doc, says, you're not thinking four-dimensionally. By the time we get to the end of the bridge, we're going to be in the future when this bridge has been built already. So if you think four-dimensionally, there is a bridge. Right? This is an example, a beautiful example, how in this case, the science or the fields of physics, which sort of this movie is sort of looking at is relativity more than quantum mechanics, but nevertheless is something that is counterintuitive. We are used to things that either exist or don't exist, but don't exist and don't exist at the same time, depending in which region of space-time you are, right? So when you hear this, you say, well, my mind is blowing. The same thing happens with quantum mechanics. But at the same time, this is forcing our minds, for the first time in our education, to think, well, probably for the second time, for those who have had a serious mathematical education, but to think without relying on what we actually see, but what we expect from intuition, but trying to follow some more general implication. The difference with mathematics is that you can rely on some mathematical assumptions and follow them, regardless whether it is relevant or not for the world. In contrast, in physics, this logical assumption that we follow to understand the world, even if it doesn't make sense compared to our intuitions, are not just speculations, they are the results of a countless number of experiments that were done specifically to verify that and have verified. So as a matter of fact, we're talking about the result of a true hardcore experimental science having been established for more than a century now. So really, we are talking about old news, but old news that still are disturbing to most of us. In the term, not disturbing in the sense that it annoys us, but still something that we have very hard time to try to make sense of. So welcome to this course. This is how we will proceed since next lecture. And I hope you enjoy the trip on the way because it will be an intellectual journey anyway, whether you will use it or not in the future. So see you not tomorrow, but Wednesday for the next, for about Thursday for the next lecture. Bye-bye. Are there any questions? Well, if not, I'll stop recording and stop talking and I'll see you Thursday. Bye-bye.